Real ultimate power right there. Real ultimate power. Okay. So this is our last unit where we're going to talk about things that are moving that are not water molecules or electrons, and that is circular motion. Good old circular motion. And when we discuss circular motion, we also want to discuss torque, center of mass, and universal gravitation. So this is the hammer throw. Has anyone ever seen the hammer throw? Okay, so you're going to know what I talk about. Okay, so I won't have to actually do the hammer throw in here, which is good, because you never really know when the string's going to break and it'll fly up and hit somebody in the face. So we're going to talk about that. This is a drawing of someone important. This is Isaac Newton. Isaac Newton. Yep. And then this. When you turn in a circle, you have very specific vectors. You have an inward acceleration vector and a velocity vector that points tangent to the circle. When I say tangent to the circle, do you know what I mean?
It only crosses at one point.
Yeah.
Yeah.
So like when you're playing tetherball and you hit the tetherball and somebody takes a razor blade and goes slice, where does the tetherball go? Straight line. It's a straight line, right? Like I hate tetherball. Slice and goes in a straight line. Okay. So some lingo. Linear velocity, that's what we've been learning so far. It's how fast an object moves through space in a straight line. Okay? Linear velocity is how fast an object moves through space in a straight line. Circular velocity is how fast an object moves in a circle. How fast it moves in a circle. And hopefully, when that person took the razor blade and sliced the rope of the tetherball's circular velocity became linear velocity. If there was no friction, then one can easily become the other. They're both measured in meters per second. It should be actually 2 pi r divided by time, so 2 pi r divided by s. So that's linear velocity, how fast something moves in a straight line through space. Circular velocity is how fast something moves in a circle through space. And the third thing you need to know is angular velocity. Angular, sometimes called rotational velocity, is how fast something spins. And angular velocity is going to be measured in radians per second, because for some reason we don't want to use degrees per second. We want to use 80 radians per second. Ask the math teachers about that. It's their decision.
Because radians are because a radian is the length of your string around the edge.
Yes.
That would be why.
Yeah. Anyway, so yeah. So if something goes around in if it makes 1 revolution per second, then it goes 2 pi radians per second. Okay? Because the circumference around your circle is 2 pi r, so it goes 2 pi radians around in 1 second. Do we need to talk about the unit circle in radians? Okay. Really quick. Well, it gives me a chance to draw a big circle. Which everybody likes drawing big circles.
Nice.
Oh yeah.
So if you start in the middle and
No.
no,
That's not the
if you start in the middle,
Right. No.
move to the right.
Yeah.
If you start in the middle, there's a radius, and that radius goes in every direction. Okay? Now, if you start at 0, we like to start here at 0, 0, then what you have here is, 1, 0. If you start at 1, 0, 1 for x, 0 for y, what you have is 0 radians. So you have 0 rads. And over here, on the other side, at -1, 0, you have a pi rad. You have pi radians. Okay. Up here, you have pi over 2 radians at 0, 1. And down here, at -0, -1, you have 3 over 2 pi. Yeah, 3 over 2 pi. Okay. So when you go all the way around, you've completed 2 pi radians of angleness.
Okay.
You've gone 2 pi radians of angleness. In space, you have traveled 2 pi r meters. Does that make sense? So if you don't know how far you go around, you just take 2 pi multiplied by r. That's how many meters you've gone around. So if you make a complete circle in 1 second, your velocity is both 2 pi radians per second and 2 pi r meters per second. Does that make sense?
Yeah.
Okay. 2 pi r meters per second for circular velocity, 2 pi per second angular velocity. Question?
And the R on the meters per second is radians?
Yes. Thank you. So we're going to basically limit our discussions to things moving in a circle today. We're not going to worry about crazy things like ellipses. We'll let Johannes Kepler deal with that. We're just going to focus on circles. So if you're studying a textbook or an internet thing and they talk about Kepler's laws of elliptical motion, we're not doing that. Not even the AP does that anymore. We're just going to play, everything's going to play in a circle. Okay, now, when things do move in a circle, we get torque. Okay? When things move in a circle, or when we want to get something to rotate, we have to apply torque. I've got a bunch of tools in here, but one of the tools, not here, in my toolbox, which is over here, I got a bunch of tools in my toolbox, and many of them are designed to apply torque, not so much force. Hammers are good at applying force, but pliers apply torque, and wrenches apply torque. Here's a wrench, it applies torque. Okay. I don't want to move my bolt, I don't want to translate my bolt in the X, Y, or Z direction. I want it to spin. So when I want it to spin, I have to apply a force over a lever arm. Okay. There's a reason you don't see a lot of wrenches this big. It would be very strange if you saw a wrench that went, that was that big. Okay. You're not going to get much torque. It's going to be very, very small. Longer wrenches will give you more torque, but they also might break. Okay, so this is my wrench. So torque, given the letter tau, it's like half a pi, tau, is used when we want to apply a force to get something to move in a circular direction, to get something to rotate, like a bolt. So what two variables do we need to calculate torque?
Length of arm.
Yeah, the length of our lever arm. So a longer wrench will give us more torque, right? So length of our lever arm, and what else? How much force we apply. Okay. So torque is a product of the force applied multiplied by the lever arm distance. Now, there's a reason that when they built the handle to the door, they put the hand bumper closer to the edge and not closer to the hinge. Why did they put the hand bumper closer to the lock and further from the hinge? Yeah, the handle.
Well, you see the black part on the handle is like the bumper.
Yeah. So why did they put this? Why did they put this on this side of the door instead of next to the hinge? Easier to push it, right? That's easy. You know what's not easy? Push it over here. Yeah. So if we had a contest and we put Corbin over here, and we put on the other side Sierra on this side next to the door, who's going to win in the door contest? Sierra. She's going to have a lot more torque. Even though I'm sure Corbin's a lot stronger physically, she's got a lot more torque. She's a huge lever arm. Okay. You know what also you can't open the door? Have you ever tried to open the door by pulling on the door? Like pulling this way? Are you going to do any good pulling this way? No. So there's one more term in our torque calculation. What's that term? If
Direction.
pulling perpendicular applies maximum torque, and pulling parallel applies no torque, what's the last term?
Angle from
The angle. It has something to do with the angle. What trig function is maximum when it's perpendicular and minimum when it's parallel? Got a 50-50 shot. Go for it.
Tangent?
Sine. Yeah, sine. Sine. I wasn't even thinking about tangent, so I guess you got a 1/3 chance. But anyway, yeah. So sine. So when you pull parallel to the lever arm, you apply no torque. When you apply perpendicular to the lever arm, you apply maximum torque. So technically, the proper formula should be FD sine theta.
Well, we're not going to use the sign in our test and stuff.
I believe there are one or two where you will. Almost all calculations will be perpendicular, but you do need to know that at minimum torque will be at parallel pole, maximum torque will be at perpendicular pole. And I can't say for sure you won't use the sign in your calculation. Okay, there is something super goofy that I'm going to mention for Tyler's benefit. Yeah. Last year, maybe it was the year before, they started giving the unit of torque in a different unit. Instead of calling it a Newton meter, they started calling it something else in the College Board. What did they call it? What other unit is a Newton meter? Go over all the units that we've had, so you can remember what unit is a Newton meter. A force times a distance. Yeah. The College Board started calling the torque unit the joule, which it technically is. A unit of torque is technically a joule, because the unit is a Newton meter, force times distance. A Newton meter is a joule, just like when you have apply a force over distance. So just FYI, should you see this in an online tutor or you want to take more advanced physics, realize the unit of torque is the Newton meter, but it also might be called the joule.
We didn't call it the joule.
I like you didn't. Yeah. I prefer to stick joule to energy. You know, there's so many types of energy, it's easier just to call the torque unit a Newton meter. But I was surprised when I started encountering that, and it's popping up. So should you find the unit of the torque to be a joule, realize that's where it came from. Okay, center of mass. Center of mass is just where all of the forces and the torques cancel out. So remember what sigma means? Sigma means all of the, sum of, means all of the torques. So a place in an object where all the torques cancel out, that's the center of mass. Which is why these crazy little birds work. You got the crazy little bird that's able to balance on its beak because there's torques in so many directions. There's a weight here that produces a torque that direction. There's a weight here that produces a torque that direction. There's a weight here that the bird itself and the tail produces a torque that direction. So all three torques cancel out, kind of like in a Mercedes symbol. Can you imagine? Can you kind of see it? A torque this way, and a torque this way. This wing is producing a torque this direction. This wing is producing a torque this direction, and the butt is producing a torque that direction. And the three torques cancel out to allow it to balance on its beak. That's center of mass. I wonder if I can get to balance up here. No.
Get the bird.
Just the bird.
I can get the bird to balance up there. Oh, that. Yeah. Okay. So just like in forces, where we have multiple forces canceling out to zero, we call that equilibrium. Well, we also call this equilibrium. So where the torques cancel out, that's also an equilibrium position. If you have a straight object that's one or two dimensions, or one dimension, the torque on the left side equals the torque on the right side. And since torque is FD, FDL equals FDR, or FRDR. in a fairly uniform object like a football, where's the center of mass? Right in the middle, right? If you work hard enough, you could probably get it to balance. However, some things are not uniform. My favorite thing's not uniform. A hammer. Okay. The hammer is made of fiberglass or plastic with a little rubber handle, and then a iron or steel head for smashing. And if you were to try to balance this, where would you balance it?
Closer to the head.
Close to the head. There we go. So yeah, there's its equilibrium point. Center of mass right there. Similarly, this is totally cool. A student did this for me. This is a bowling pin. Where do you think the center of mass of a bowling pin is? Where would it balance? Bowling pins are designed to spin. It's kind of cool. They're designed to spin and basically knock down the pins around them. So the center of mass for the bowling pin is the hump, right there. It's not in the middle. It's the hump.
Okay.
So my question for you is this. This person cut the pin not exactly at the hump. Kind of, beggars can't be choosers. A parent did this, so it's pretty good. I really appreciate that it happened. But if you were to weigh these two pieces, would they weigh the same? Why don't you talk to your neighbor? If you were to cut the bowling pin where it balances, right there, okay, if you were to cut the bowling pin where it balances, would the two pieces weigh the same? Talk with your neighbor. Take a minute.
Yes,
Yeah.
unless you actually, if you can set distance, because if you have a super long stick and a little tiny weight on the end, and you have like a big weight on the other end,
It's not going to be the same on either side.
because if you look at the height, there's less mass farther out.
Yeah, you're right.
No.
All right. If you think your options are long piece heavier, short piece heavier, or the same. If you think they would weigh the same, raise your hand. 1, 2, 3, 4, 5, 5. Okay. If you think the long piece would weigh more, raise your hand. 0. So the other 12 of you think that short piece would weigh more? Interesting. Who can tell me why the short piece would weigh more? Robbie? Robbie's fastest.
Because when it's force times distance, the one on the left is longer. So as long as the ratio is
Exactly right, yeah. As long as the FRDR and the FLDL are the same, is that what Adam said? Adam just gave you the answer? Oh, okay. Yeah. Okay, so as long as the product of the two are the same, then they'll be in equilibrium. So 1/2 has a bigger D than the other half, right? So if one has a bigger D, it has to have a smaller F. Bigger D, larger F. And what are the F's? They're just gravity. Okay. So the shorter piece would have to weigh more because it has a smaller D. Nothing wrong having a smaller D. The effect is massive when you look at the hammer. It's kind of neat. This gets people. So if you're like, okay, so it balances right there, which is going to weigh more, a large chunk of steel or a piece of plastic? Most people would say, which would weigh more? If I cut my hammer right here, what would weigh more? Yeah, a large chunk of steel, and it would be really obvious too, because look at the huge D here. That's a big D. You've got to be proud of that D right there. Hey, so meter stick. Where's the center of mass of a meter stick?
50 centimeters.
50 centimeters, 50 centimeters. Where's the center of mass of a hammer?
About an inch from the hand.
Near the hammer's head.
Inch from the head.
Where's the center of mass of a bowling ball?
Center.
Right in the middle. Sphere.
Slightly
Yeah.
to this side if you're including the holes.
Exactly. Slightly towards the holes, but for the most part, pretty close to
Isn't
like
it
my
sli-
center.
Isn't
Yeah.
it slightly away from the holes?
No, it'd have to be closer to. You're right. Slightly away from the holes. Yeah, because there'd be more mass on that side. Slightly away from the holes. And then C-clamp. I love C-clamps. There's one right there. Where's the center of mass of a C-clamp?
Which direction are we balancing?
I'm balancing it flat. So a C like this. So like this. If it was into the plane, where to balance? It's in the hole. Yeah. It's actually right there. Yeah. The center of mass of a C-clamp's right there. You can't balance a C-clamp flat. You can't. It's impossible. Because the center of mass is where it doesn't exist. Okay. So let's talk about circular motion. Just like with vibrational motion, with harmonic motion, circular motion has periods and frequencies and amplitudes. Period is still the time for one cycle, but now it's the time for one all the way around. Instead of one back and forth, it's the time for one all the way around. And frequency is what times period, or what multiplied with period. Frequency and period are what?
Inversely related.
Mathematical inverses. So period is still the mathematical inverse of frequency. Frequency is still the mathematical inverse of period. So if period is how long it takes to go one all the way around, frequency is how many all the way arounds you get in 1 second. Engines are, they spin their cylinders with RPMs, revolutions per minute, but you can turn those RPMs into radians per second if you want. A radian per second is a frequency. It's how many all the way arounds, well, a 2 pi radian per second is a frequency. How many all the way arounds you get in 1 second. Path traveled is the circumference of a circle. We talked about that. A circumference is 2 pi r. Direction of velocity vector is tangent to the circle. We talked about that. So if linear velocity is distance divided by time, then circular velocity is circumference divided by time. Circumference is 2 pi r. Time is period, 2 pi r over t. So circular velocity, as in velocity through space in a circle, is 2 pi r over t. And this is where we spend most of our time. Because planets move through space with a speed of 2 pi r over t. Hammers in the Olympics move through space with a velocity of 2 pi r over t. Tether balls, 2 pi r over t. Especially if you're good at tetherball. Especially if you have mad tetherball skills. Sorry, I just got Nate going again. Okay, so the direction of velocity is tangent to the circle. But what keeps it from flying away?
The string.
String, right? The string keeps it from flying away. So if I was to spin this ball, by the way, tape has been removed, so I'm not going to spin it really fast. In case it flies off, I don't want to do too much damage. What direction do I have to pull to keep this from flying away?
The opposite direction.
If I let it go, if I stop applying the force, it's going to go in a straight line, right? But what direction do I have to apply on, what direction do I have to apply a force on that string? What direction? Towards the center. I have to apply a force towards the center. If you ever see the picture or the hammer throwers have to pull inward. They have to pull inward. So they have to create an acceleration to do the turning. And the acceleration is directed inward to the circle. In fact, perpendicular to velocity. When we looked at vectors, we did vector simulation, you might remember that when you had to draw the J, or you saw something moving in a circle, the acceleration vector was perpendicular to the velocity vector. When that happens, you get a turn. When they're not perpendicular, you get an ellipse. You get an ellipse. But when they are perpendicular, you get a circle. And this is one of those things, once again, here's for Tyler's benefit. As an object moves around a circle, is its velocity changing? If you're not applying any additional force, if it's moving around a circle, is its velocity changing? Yes. Is its speed changing?
No.
No, because speed is just how fast. Velocity is how fast and where. So the velocity will constantly be changing as it goes around the circle, but the speed will be the same. The acceleration vector will also still be changing, because it will always be pointed toward the center. It'll be constant in magnitude, but it will be changing in its direction. Oh, sorry, are we ready to move on? Okay. And the hammer throw. I wish I had an animated GIF for the hammer throw, but I do not. All I have is this guy. We'll call him Bud. So Bud's got the hammer, and he's spinning it around. Around and around and around. How does Bud make the hammer go faster so it can go further? He spins faster. That's easy.
He keeps it towards the outside edge.
He keeps it towards the outside edge. But if all you have to do is spin, then any of us could basically kick butt in the hammer throw. I can spin pretty fast. I bet you can too. What's more than spinning? What's the key thing in the hammer throw? Yeah. Yeah. You have to pull in. And the faster you spin, the more you have to pull. So he's exerting a force in what direction? In. He's pulling in. I mean, you can see. Look at these massive biceps and pulling in and latissimus dorsi. That's these guys. Okay. So he's applying a force in, and since the hammer has a mass, he is creating an acceleration inward. That acceleration is given a small letter c to represent what? Centripetal. Like the petals of a leaf. Do not confuse centripetal with centrifugal. Centrifugal or centrifugal doesn't exist. Doesn't exist. It is centripetal. So next time you're like, well, due to centrifugal force, no. That's exactly what it is. If you take a bucket, anyone ever seen the bucket go around and around? Okay, I don't have a bucket. No. I just don't want to do it. But anyway, so there's this thing you can do, and usually science teachers do if they're good. Unfortunately, you got me. So you got a bucket, and the bucket has a handle, and then the science teacher holds the bucket, and the bucket swings around in a circle, and the water doesn't come out. You're like, woo, look at me. Here's the thing. If the bucket, and what again, the water doesn't come out. Have you seen this? Like swing it around, water doesn't come out? So next time someone does that, and you're like, wow, that's impressive. Fill the bucket up top. Fill the bucket all the way in. Could you do it if the bucket was filled all the way? No. You could not. Because what you don't see, and they never use a clear bucket, is the water is not down here. The water is over here. It's inertia that's keeping the water in the bucket. It's the inertia because as far as the bucket is concerned, where does the water want to go? Out. It wants to go out. I guess the water goes away. Yeah, the water wants to keep going out. It wants to keep going out. The water's like, oh, good. We're going to keep going. Oh, I'm turning again. Oh, I'm turning. I'm still turning. So, yeah, next time you want to do that, like, ooh, that's impressive. Now fill the water up to the top. You're not going to be able to do it. Okay. So, centrifugal doesn't exist. It's just inertia. centripetal definitely works. So, as the thrower increases his tangential velocity, how does the force exert on the hammer change? As he speeds up, he has to apply more acceleration. And to produce that more acceleration, he has to apply more force. So there's probably a formula, right? Want to derive it?
Sure.
Neither do I. So we're just going to remember that there's a formula, and I'll give it to you here in a second. There's a formula that relates how fast you want to go to how much acceleration you must produce. And it is that. AC equals V squared over R. So AC equals V squared over R. If you're sitting up front, it's right there. So those are sitting up front and like, oh yeah, I can cheat. I can just use the formula right there. But I don't want to derive it. You can derive it if you want. You can get on Hyperphysics or watch it on YouTube and they'll show you where it comes from. I just like to remember that AC equals V squared over R. And of course, FC equals MAC. These two are big ones. Big ones in circular motion. Big, 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 big. The bottom one is just a derivation, plugging in V squared over R for A. So these are the big ones. AC equals V squared over R. FC equals MAC. This is just Newton's laws. This is a derivation of angular velocity divided by mass. So if you have a set radius, what this really means is if your radius is set, and I'm assuming the hammer isn't elastic, it's usually a chain that doesn't move. If your radius is set, if you want to produce more A, or more V, you're going to need to produce more A. And by producing more A, you're going to need to produce more force. More force in the hammer means faster velocity. In fact, if you were to somehow double the amount of force you could apply, your velocity would what? It would quadruple. Yeah. And then when you let it go, it just becomes a projectile. You want that initial V to be as fast as possible, because then it just becomes a projectile. And because it's big and massive and heavy and smooth, usually it does a pretty good job of ignoring air resistance. Okay. Questions? Conservation of angular momentum. I didn't get a chance to oil this thing, so we're going to give it a shot anyway. Looks like it should be okay. We're gonna watch Mrs. Byers go to the hospital. Okay. Need a volunteer.
I'll volunteer.
All right. All you have to do for this first part is give this arm a little bit of a shove. Keep me spinning, doesn't matter. Okay, you got it. Try it again. Mob balance. No, it's good. Mob balance ain't too good. Anyway. Okay. Anyone else want to try it? Okay. There you go. Try to center yourself over the wheel. Yeah, it helps if you imagine putting yourself a little bit forward so your butt is lined up at the center. Yeah, a little bit forward helps a little bit. Let me try it. Here. Here, get back on there. I'll give you a push that won't throw you off lopsided. Okay. Now bring it in. Whoa! Okay, so I'm going to leave that there all week. Try not to wound each other. So be cognizant of your environment. But it's pretty fun. So these are just 5-pound weights. Okay, so you can get some serious gains. And I'll leave the disc right here, and you can play with it. So what was going on? What was going on? What happened?
The radius was greatly decreased.
Okay, so your radius was great, so there was a little bit of friction, but your radius was greatly decreased. So, did his mass change?
No.
No. By bringing it in, his mass didn't change, but what did change is where his mass was located. So, spinning masses is very, very strange, because if you just sit in your chair, your mass doesn't change. But if you bring your arms out, your mass doesn't change, but where it's located does change. Okay? You ever seen Tony Hawk do his flip? When he goes up and do a 720 sick air, he gets really, really small. Okay? So when you go up to get some sick air on your skateboard, you want to make yourself as small as possible. Divers do the same thing. Divers go out like this, and they tuck, and they start spinning, and they untuck, and they stop spinning. Okay? So it has to do with where your mass is located. That's called rotational inertia. Rotational inertia is your mass and where your mass is located. Now, angular inertia. Angular inertia is a property of your mass and where that mass is located. Now here's the crazy thing for Tyler. Angular inertia for a disk is different than angular inertia for a sphere, is different than angular inertia for a ring, is different than angular inertia for a cone. They all have different angles of inertia, but generally the value or the formula we use for angular inertia is mr squared. M for the mass, r squared for where that mass is located. Basically, if we were to split someone in half, whoop, their center of mass for each side is where the r would be. Okay? So when you split me in half, and I'm holding the weights like this, my center of mass is probably like right here. But if you split me in half and you move the weight over here, my center of mass moves just an inch or two. Does that make sense? Okay. So that's what's going on. So similarly, if you throw this hammer, it's going to spin over its center of mass. Okay? If you were to take somehow, so you spin it, boom, you throw it, it spins. If you were to take the head here and move it to the middle, so the head was in the middle and there was two, like this part, this plastic part, would it spin faster or slower? If R decreases, you reduce inertia. Remember, acceleration and inertia are related. By reducing mass, acceleration goes up. By reducing inertia, velocity goes up. So it spins faster. So you know all those guys who are like, oh, I'm going to put these giant wheels on my car. I'm going to swap out my 16s for 19s. It's going to make my car go faster. How would you respond to that?
Nope, you're wrong.
No.
But they look cool.
It would look cooler. Yeah. Actually, your wheels would have to overcome a lot more angular inertia. So angular velocity is how fast you're spinning in radians per second.
Yes, I'd like to.
And angular momentum is conserved. Just like linear momentum is velocity times mass, P equals mv. Linear momentum is mass times velocity. Angular momentum is angular mass times angular velocity. So linear momentum was P equals mv. Angular momentum is angular mass times angular velocity. looks like where we're going to stop today. Momentum is conserved. Any questions before we wrap up? Okay. So again, angular inertia is like rotational mass. It's mass-like. Angular momentum is conserved, and that's the quantity of angular inertia times angular velocity. Just like linear momentum is mass times velocity.